Okay, so welcome everybody to this program finale for the first year of the Simons NSBP Scholars Program. Before we get started, I just want to give you some logistics about how the program will run. And so we are going to start out with a brief introduction by Professor Stefan Alexander. He's going to describe the program and give some words of wisdom. We will then move to presentations by each of our scholars. And I will give more information about that when we get there. And then after each scholar makes a presentation, we will conclude the finale with remarks from David Spergel, who is representing the CCA and the Simons Observatory. So with that, I want to turn it over to Professor Stefan Alexander.
Hi, everybody. My name, of course, this is Stefan Alexander, and I'm the president of the National Society of Black Physicists. And it's a real pleasure and honor to be in this position right now. We made it, we did it. It's the first thing. And so this is like, give ourselves a round of applause. I definitely want to applaud the students and thank the mentors for all of your passion and hard work and dedication, especially given these times to work with our NSBP scholars, Simons scholars. I also want to give thanks to Dr. Jim Simons and Marilyn Simons for their unending support of this program. We acted very quickly and swiftly, and we're just very thankful for that commitment from the Simons Foundation. I want to thank Casey for all of the hard work and the staff for seeing that the day-to-day operations and of this program ran so beautifully and smoothly. And kind of want to maybe start with a quick story here, because y'all know I like to tell stories. And it starts with November of last year. And the moral of the story actually is about action. There's a lot of words these days, words of like, we want to do certain things, we want to do things in the name of social justice. But at the end of the day, it all has to come down to action. And before there was before the pandemic hit us early this year in the United States, way back in November, at the National Society of Black Physicists, our annual meeting in Providence, early in the morning, on a Saturday morning, Jim Simons flew out to Providence to come and hang out with all of us, hang out with the National Society of Black Physicists and meet with the students and give a keynote talk. And to me, that was a statement of sort of already the commitment that he has. And that kind of allowed me to sort of realize that, the NSBP has a true ally in the Simons Foundation. So, and that doesn't, end there, of course. I mean, when the pandemic hit and much later on after the aftermath of the George Floyd situation, very quickly, David Spergel, who is the director of the Center for Computational Astrophysics, who will be speaking later on, and Brian Keaton, who is the director of the Simons Observatory, we got on the phone right after that moment. And our conversation was centered around what can we do? What can we do? We know there's going to be a lot of students who are going to be sitting unemployed this summer with a lot of potential. And because of our passion for science and research, we knew that this would be an opportune time to get y'all involved with mentors in this program. And at the time, it seemed that will we be able to pull it off? But everything came together, and people behind the scenes came together so that you all could engage in what I hope will be a fulfilling summer of research, and that now you're all on your way, hopefully, to maybe even thinking about applying to, going into PhD programs and continuing on this exciting career of being a research scientist. So on that note, I want to thank you all. I want to also thank the NSBP board, who also worked very hard to help make this happen and collaborate with the Simons Foundation, and the NSBP Student Council. And I want to also welcome you all to the NSBP family. This story will continue on, and I think that this will be I think looking back in time, we'll clearly see the fruits of this and see that we've also made a little bit of history. So thank you for having me, and I'm looking forward to hearing all your talks.
Fantastic. Thank you, Stefan. So next we're going to move to the real reason why we're here. As much as we like Stefan and he has great words of wisdom, we came to see our scholars talk about the fantastic work they've been doing. And so we're going to have a series of talks. Each scholar will present their work. If you have a question for the scholars, you can ask those questions by hitting the Q&A button that is on your screen and typing your question. The scholars will attempt to answer your questions in the chat. If they do not have time to get to your question, or for any reason, all of the questions will be recorded and we will follow up with answers to those questions. So with that, I think we're ready to move on to our first presentation. And so this will be from Teresa. So Teresa, if you could unmute yourself and take it away.
Hi, everybody. I'm Teresa, and my project this summer was building codes for detector module validation. This was in conjunction with Simon's Observatory. Suzanne Staggs was Aaron Healy's advisor, but I worked mostly alongside of Aaron and Zach with this code. So my job of the summer was to create a universal shorts diagnostics code for the DC wafer for Simon's Observatory's detectors. The detector module is made from silicone wafers, and the metal wiring is kind of plastered on top of it, like a sandwich. And these detectors are packed very tightly together, about 2,000 per plate, about 2,000 per wafer, and every wafer is about the size of a dinner plate. So we modeled this electrical lines in the system, as you can see. I'm not sharing screen, what am I doing? You can see it's modeled in the upper left side of the screen. So we had to model it as a system of 5 equations. You can see it goes left, right, up, and down. And once we finished this project, the output of this research could be used for other things besides this specific issue, this specific problem. So our issue was that since the wafers were so densely packed together, they kept when you have a system that's so close together, it keeps shorting out. So my job was to figure out how to predict where the shorts were through the universal shorts diagnostic code. And on top of finding out how to fix find out where the shorts were in the code, you can also figure out other things about the system by inputting different numbers. So it's not even just about fixing the shorts anymore. It's about finding out more about the system on top of fixing the shorts. Some of the systems that we used for this was Python, because that was where the code was built in. And we also used Layout Editor because we also had to measure the shorts to figure out how long they were. Yeah. So one of the things that I learned about in this project was, a more comprehensive understanding of how to code. I wasn't really given much of a chance to do it in my undergraduate, understanding it in a more comprehensive, larger level, because most of the things I've worked on were more theory-based, more like actual like geology, astronomy-based, but never anything that was so like hard-coded. So I did learn a lot more about Python with this project. I learned a lot of problem-solving skills. Case, can you go back to the other slide? Just for a second, just for a quick second. So in the bottom right of the corner, we plotted the bias lines, which were you see these very intricate lines going across the wafer on the left. They're represented in the graph on the right, and the dots that are colored with the line represent the different turns every line takes. But the different colored dots represent the shorts that were projected to be found. My idea was to connect lines, and so you have a stronger visual representation of where a possible short could be. So with this, we have a more accurate representation of where the shorts could be. You back to the other side. in my undergraduate degree, I wasn't very good at E&M. I learned a lot about electricity with this project, and I also learned a lot more about linear algebra because that wasn't really a comprehensive part of my undergraduate education. So with this project, I learned a lot of really useful skills that I'm going to take with me for the rest of my academic career.
Fantastic. Thank you, Teresa. So next we're going to move on to Winston.
Hi, my name is Winston Harris, and my project was on the determination of exoplanet periods based on rate of velocity data. Next slide. So the goal of my research was to use rate of velocity data to determine the period with as few data points as possible. And for this, well, I was assuming it was a two-body system where both the objects were orbiting around a center of mass. And with rate of velocity, how it works is an observer will detect the Doppler shift of the light coming off of the star. And you can use that to say if it's determine what the velocity is. If it's blue shifted or red shifted will be if it's retreating or coming towards the observer. Ideally, the rate of velocity should be a sinusoidal wave. Next slide. So with the data points that I collected, I used a program that uses a Markov chain Monte Carlo process to narrow down which sine curves best fit all of the data. And I determined that when data span multiple cycles, it returns the approximate value of the period more efficiently. The calculated period that I got was less than 1% different than the actual known period of the exoplanet that I was looking at. And the smallest number of data points that I got was about 8, and I needed approximately 2 periods or longer to determine the period efficiently. The more of a span of time that the data points covered, the quicker the program was sure that it was on the period. Now, some things that I learned were I used Python notebooks for the first time, and that was something that I got a lot of information from. I also learned a lot about Bayesian inference, which uses prior estimates to better inform future processes. And I would say that this whole program has made me realize that I actually do like research. This is my first positive research experience, I would say. For sure, net positive research experience. And because of this program, I am like dead set on pursuing a PhD. That's it.
All right, thank you, Winston.
Wonderful, wonderful.
All right, so next is Anansa. Is Anansa on? I know, so Anansa has a very quite tight schedule with her classes, so we can come back to her. So Nico, short notice.
All right, hello everyone. If you can hear me okay. My project was on this strange theory of gravity called Chern-Simons modified gravity, which, where have I heard Simons before? It's the exact same Simons as Dr. Jim Simons, whose name we're seeing all over the place today. So if you'll go to the next slide, please, Casey. So what this modified theory of gravity does is that it takes the normal Einstein-Hilbert action, which is the underpinning of all of general relativity, and is this very, very basic action, and adds this Chern-Simons term onto it. Now, why would we want to add anything onto general relativity? It already works so well. Well, there's a few things that this term does. So the first thing I want to mention is that it's a topological invariant, which means that it encodes a lot of completely global information about your space-time. And so it's explicitly independent the metric you're working with. And in physics, we're all over invariants. We like using invariants. They're very attractive to use, but this one has a little bit more to it as well, which is that in string theory, it does something special to include the scalar field coupling in this Chern-Simons term, which is that it cancels the axial anomaly, which is a fancy way of saying that this scalar field, which is exactly the axion field, which you may have heard about before as an extremely attractive candidate for dark matter, it basically makes symmetries a lot more clean in string theory. And as well, it's the axion field. It's this field in quantum field theory that describes one of the most attractive candidates for dark matter. So what we did with this action was to jump off from some work that some guys from Kyoto University did, which shows that if you go through and derive an equation for the orbital velocity of a black hole in a specific metric in this space-time, assuming conserved angular momentum, conserved energy, things like this, you get that there's a correction to the orbital velocity. And if you know anything about dark matter, you might know where this is going, which is that if you have an added term to this orbital velocity, you might get a flat rotation curve, which is what in the center this plot is from. It was some data I had on hand from 21 centimeter emission from 3 to 8 kiloparsecs. And I used some constants in this orbital velocity expression as fitting parameters, which is what the J and K are. So what I then did with those fitting parameters was to produce geodesics, so that we could actually look at something and be able to tell what this theory is doing. And that's what we can see on the right. On the top is a geodesic in force field spacetime, which is for a stationary, not spinning black hole. And on the bottom is the same thing, but in this Chern-Simons modified theory. And you can see fairly clearly that there's a very significant correction to this, that it spins a lot. It goes around the black hole many, many more times. So what was the point of this? What happened in this project? So I learned a lot of physics, obviously, but I think one thing that was most significant to me was that I learned a lot of general relativity while I'll be taking that course for the first time in the fall. So I learned a lot of skills that'll be particularly pertinently immediately useful for me. And one thing I'm very hopeful about is with this project, I'm going to continue with Professor Stefan Alexander on this second equation on the left. It's a complicated partial differential equation that we're hoping to solve numerically to be able to get a sort of picture of what the axion field does dynamically around a black hole in this metric. And as far as NSBP, as a student representative of NSBP on the student council, I'm hoping to be more involved in projects like this, where where students are benefiting directly from the connections of NSBP. So yeah, that was my project. Thank you very much.
Great, thank you, Nico. All right, so next up is Rebecca.
Hi, everybody. I'm Rebecca. This summer, I worked with Rodrigo from the CCA on a project of modeling star spots and determining differential rotation of the spots as part of the Simons NSBP Scholar Program. So star spots are observed on our sun, and there's evidence from Kepler that other stars also have these spots. Nobody really knows exactly what causes them, as it is an area of active research, but we do assume that their presence is magnetically driven, where the magnetic field suppresses convection, preventing hot material from the stellar interior from rising to the surface, thus causing these dark observable star spots. It's important to note that star spots do rotate at different rates depending on their latitudes. Higher latitudes rotate at a slower rotational period than spots near the equator. We call this differential rotation. Here's an animation of the star we have modeled synthetically in Starry. It has two different spots experiencing differential rotation, and both of these spots have different sizes and different brightnesses. In order to achieve our goal of correctly modeling the M-dwarf GJ1243, we spent a lot of time working with synthetic data. By working with a fake star modeled in Starry with known star spot parameters, we were able to check the work of our model. It's super important that we know that our model works correctly because we won't always know what the actual position, size, and brightness of our star spots are because we can't always see the surface of the star we're trying to work with. Here you can see that our model has been optimized to match the data. The next step of our process is to recover the true star spot parameters by using a statistical process called MCMC. Next slide, please. The results of the model we created to determine the characteristics of star spots can be seen on this corner plot. The blue lines indicate where our known true parameter values are, and the darkest portion of the plots indicate where our model found the true values to be. This plot was super exciting to create and see because it tells us that our model actually does work and that we're able to apply our model to real data. So this project was really fun to work on. I actually really enjoyed the process of learning science and learning how to code at the same time. I actually do start classes on Monday, but I think it would be great if Rodrigo and I could keep working on this project around my class schedule, as I really did enjoy it. And I think that the process of modeling this is really exciting. This summer was seriously fantastic. Without it, I think I would have been really bored and lonely in my house trying to avoid COVID and just trying to stay sane while I waited for courses to start. And I think working on the summer research project really helped solidify my decision and kind of validated my decision to go to grad school because I know that I truly love physics and I've made the right choice. So thank you to everybody who made this possible.
Thanks, Rebecca. That was great. Okay, so next up is Aiden.
Hi, my name is Aiden Simpson, and my project focuses on the evolution of stars within AGNs. Next slide. So the area of space where this project is focusing on is the region around a supermassive black hole at the center of a galaxy, also known as an AGN. A black hole is active when matter is falling onto it in the form of a disk around it. It is possible for stars to end up in this region in two ways. Either the star is formed inside the region, or the star is formed in a different region and then captured by the disk through slow loss of momentum as it passes through the disk. The star's gravitational force attracts the matter from the disk, causing it to accrete onto the star. This can affect how a star evolves. Typically, higher mass stars have a shorter lifetime than the lower mass stars because they burn brighter and run out of fuel faster. And more massive stars can also fuse heavier elements. Next slide. So the goal of this project was to simulate a star in this region of space. To do this, I learned how to use a one-dimensional stellar evolution code called MESA, and I used Python for the data analysis. What the simulation does is it replicates the conditions in this region, and it allows a star to evolve within this region. As you can see from the first graph, the graph at the top, the star starts gaining mass at an increasing rate. This is because as it accretes mass, it increases its mass, which increases its gravity, which increases how much it accretes, and so on in a runaway process. The star also starts losing mass towards the end of the simulation, and this is because the star becomes so luminous that the radiation pressure of the star becomes greater than the gravity holding the star together, allowing mass on the surface of the star to begin levitating. The luminosity where this occurs is also known as the Eddington limit. When the star loses its mass, some of its mass, it can pollute the accretion disk with heavier elements. The second graph on the left, the bottom one, shows the evolution of the stellar core composition of the star over time. The blue line represents how much of the star's core consists of hydrogen, and the yellow line consists of the star's core, how much of the star's core consists of helium. The star burns through its helium extremely fast relative to other stars of the same size. Next slide. This program has meant a lot to me. I've had the opportunity to learn from so many different physicists about a range of topics in astronomy and astrophysics. I also had the opportunity to be able to apply the things that I've learned in some of my astrophysics classes. I have to thank my outstanding mentors who have always made sure that I understood the physics behind what I was doing, and they were always there to help me on Slack and through the meetings. And also through other talks, they provided me with great resources to help me prepare for the future, whether it's classes, internships, grad school, etc. So yeah.
Cool. Thank you, Aiden. So next up is Dante Milner. Dante, you want to unmute and go to town?
Yes. Hello, my name is Dante Milner. I am a junior and astronomy major at Eastern Illinois University. Next, please. I had the opportunity to work with Cornell University and also as well as the Science Act Observatory collaboration. They have developed a way for students to learn about the cosmic microwave background. As you see to your right, they use a program called Jupyter, which allows for open source coding. They were able to create interactive blocks of code for learning purposes called the cosmic microwave background, called the cosmic microwave background notebooks. And also in the bottom right, you see there, two students from Cornell University, Kashama and Pedro, developed a website called the Cosmic Microwave Background Supplement. The supplements are meant to act as a companion guide to students who are learning about the notebooks, Next, please. As I said earlier, the notebooks were primarily written by Cornell University and also by the Science Observatory Act collaboration, but more specifically, were written by Jeff and Renee. And to your left, you see that is an example of what the notebooks look like. And for my project specifically, I was asked to go through and learn the cosmic microwave background myself by using the notebooks and the supplements, and to provide my feedback as someone who is not an expert in the field at all. Next slide, please. What I learned from the notebooks and from the supplements, the things I took the most from this project was how to utilize code to create different maps of the cosmic microwave background, noise filtering such as white noise and atmospheric noise, the Fourier transformation, and also the Sine-Zolcius effect from galaxy cluster. Next, please. To your right, that's a gigantic block of code, and that's basically an example of coding called the Fourier transformation, which is basically me taking a sine wave into an actual graph that can be read. Next slide, please. What I learned from the NSBP and my future thoughts. I gained a better understanding on how to get into grad school, learning specifically about the general and the physics GRE, and also how to get into grad school when you don't have the best scores, when you don't have the best GPA or the best GRE score. And the thing I enjoyed most from the program was definitely the professional development meetings. Next, please. And for my future hopes, I hope to continue gaining research experience. I also hope to gain more experience in doing summer research, whether that be with NSBP or at a REU. I also hope to one day attend a NSBP conference, and I hope one day to, I don't know, maybe meet my fellow scholars in person, whether that's again at a NSBP conference or just somehow out and about through the work field. And I again want to thank NSBP for giving me this opportunity to work with Cornell over the summer, and thank you.
Great, thanks, Dante. Okay, so up next is Alyssa.
Hello, my name is Alyssa. I go to Humboldt State in California. My mentor this summer was Kevin Huffenberger from Florida State University. So my project was about SC galaxy clusters, and I studied dust emission in Planck data. So what I was doing was I was looking at the positions of galaxy clusters from the ACT data products, and I was looking at the position of these clusters in the Planck legacy archive data at 353, 545, and 855 or 857 gigahertz to look for dust emission. Next slide. The reason why we were looking at dust emission in this frequency between 300 and 800 gigahertz is because there's a lot of stuff we're observing, but in this specific frequency, we only see dust. So we're using the ACPOL cluster catalog and Planck legacy archive maps. And I got to use this software called TopCat, which helped me learn about like other softwares that you use in sort of the astrophysics field. And then to the right is just a graph that's illustrating that there's like a lot of stuff that's being observed, like synchrotron emission, thermal emission, dust emission. But for the purposes of this project, I was only focusing on dust emission. Next slide. So the software that I was using was mostly Python, and in Python they have this thing called HealPix, and it's basically it's called the hierarchical equal area isolatitude pixelation scheme. And what it does is it breaks apart a sphere into equidistant or equal parts, and use HealPy, which is a module in Python, to handle the data. So next slide. So in HealPy, I was able to start using these positions of galaxy clusters and zoom in on them. So what we're looking at now is called a gnome view projection of the El Gordo and the Virgo clusters. And they're some of the largest galaxy clusters known. So next slide. And so big part of this process was, so once we're looking at the positions of these clusters, we have to do something called match filtering. And match filtering is a process for detecting a known piece of signal or wavelet that's embedded in noise. So in my project, I worked with grad students, Gabriella and Carlos, who really helped me to understand sort of like how to implement this process in Python. So next slide. So match filtering, what it does is it helps us to correct for dust emission, because when we neglect to correct for dust emission or some of these other things in the air, they affect the mass of the SC clusters, which can affect our catalogs of data. Next slide. And so a really great thing about this project was I got to use Python, I got to use other Astro software like TopCat, Aladdin Light, and then also HealPix. And I basically also got to learn about some really important image and data visualization techniques. I also got exposure to research group settings and dynamics. Every Friday, they have a research group meeting. So that was really, really cool. And that's kind of what inspired me to be like, I can't do grad school. It's hard, but everyone kind of works together because there's undergrads in the group. There was a high schooler in the group. And my mentor, Kevin, was like really great about sort of making the whole group feel like a team. So I also had access to grad students. So I got to ask Gabriella a lot of questions about like, what is grad school like? How hard is it? What classes did you need to take beforehand? Which was really helpful. And then this project, it's also just a great pathway for future Cosmo research. So 2 weeks ago was the CMB S4 conference, and a lot of the talks were in my head, but it was amazing. They actually started with a session about, let's talk about anti-racism, which was amazing because my thing is most of the spaces that I've been in physics-wise have been mostly white. And so it was really great to have this moment where I was like, we're talking about what it's like to have people that are different from us be in a research setting. So it calmed my nerves a bit, especially amongst considering grad school and leaving home and all these things. Sorry, next slide. And so research in the time of COVID, I think this was super useful because I got to strengthen my Python and my Mathematica skills, but I also, like, remote learning is a great collaborative tool. I mean, the research group I worked with was in Florida. And more important, just exposure to research, because there aren't really opportunities at my school. So this was a great way for me to sort of like build my skills so I can get ready for grad school, because I'm definitely going to apply. And I just want to say big thank you to Casey, and then to Kevin, and then the rest of the group, and then also the scholars, because you guys have been amazing. Thank
Fantastic. Thanks, Alyssa.
Apply to Brown, Alyssa.
you.
Oh, sorry, there was a slide there. Okay, so next up is Jess.
Hey everyone, I'm Jess Foylan from Whitman College, and this summer I've been really lucky to work with Matt and Oliver on the effective HALO model and comparing it as an analytic method to a simulation. Next slide. And so before I get into what I did this summer, just want to talk about a funky little particle called the neutrino. It was initially predicted to be massless, but further research found out that it was in fact not. It has 3 known flavors at this time, and each flavor has a different mass, and so there's no absolute like certain mass that we have for each of these flavors. And since there's such a mystery, just seeing how adding massive neutrinos to our analytic method of the effective HALO model and seeing how it affects the power spectrum is really helpful, because honestly, any information on neutrinos is very helpful, since they're just really mysterious, and they're very, very, very tiny particles. And so the effect, like a challenge that we ran into, was that their effect on the power spectrum is also very, very small. So we had to definitely zoom in on the plots to actually see anything useful. And also, this is a funny little cartoon to exemplify how we don't know their weight. And so next slide, please. And so what I did this summer. So like I said, we looked at how the effective HALO model, or EHM, stacks up to some of the Quixote simulations that have been done before, once we add massive neutrinos. And so from the graphs, I had like the no neutrinos at all, and then on the right, I have, if we add neutrinos that are collectively 0.4 electron volts. And so as you can see, the change is very small. If you specifically look at the effective HALO model, the red line on the graph, you can see that it does change, but not by much. And so some fitting for the graph that I did was I had the effective HALO model and like just the different power spectrums, and then I subtracted the simulations just to see the difference between them. And from how close the red line is to the 0 line, or the 0 value, you can see that the effective HALO model does pretty darn well in with handling, or like just fitting it compared to simulations. And the other graphs, which are nonlinear HALO fits and the linear matter power spectrum, don't do too well, but yeah. And so just moving on to like more reflection on the program, I would say that this program has been like very helpful for me as the only Black student pursuing a degree in physics at my college. It's been really refreshing just to see other scientists like me, and just to hear all these professionals just talk about their work and just revitalize my love for physics and astro, which has been really helpful. And also to have like additional programming background with like just Python, and getting that skill was very helpful, because I thought it was good before, and then I did this research, and there's always work to do. But yeah, and then in the future, I hope to continue working on this during the semester as I go into my senior year. And then like again, with this program, it's shown me that I can in fact do grad school, and that it's something that I should pursue, whereas before I was kind of like, eh. But I'm excited for what the future holds for me. And I'd like to thank everyone, especially my mentors, for all the coding questions that I've had. And yeah, that's all.
Great, thank you, Jess. Okay, so next up is Dante Jones.
My name is Dante Jones. I am a Simons NSBP scholar, and I spent this summer testing the Einstein equivalence principle with the Atacama Cosmology Telescope. Next slide, please. So what is the Einstein equivalence principle and what are the consequences? So the equivalence principle is one of the two main ideas that Einstein used when he was developing the general theory of relativity. And essentially it says that any photon moving through a gravitational field should travel at the same rate regardless of its energy. And a consequence of general relativity is that any photon moving through a gravitational field will slow down. And this phenomenon is known as the Shapiro time delay, and it's something that we can measure with the first equation there on the right, where delta t is the time delay, gamma is a parameterized post-Newtonian parameter, c is the speed of light, and then the integral is the gravitational potential being integrated over the path from the source of emission to the source of observation, which is the Earth. Now, if two photons were emitted from the same source, they should then arrive at the same time. And if they don't, then there's a violation of the equivalence principle. So we can test this by measuring the resultant Shapiro time delays of photons with different frequencies using the equation there at the bottom right. So measuring the violations. According to general relativity, every gamma value should be equal to just 1. So the difference between them should always be equal to 0 in accordance with the equivalence principle. Now, the limits on violations of the equivalence principle are characterized by limits on delta gamma. So the closer to 0 we can get, the more accurately we can constrain these equivalence principle violations. And the Atacama Cosmology Telescope, or ACT, it is a fantastic tool for doing just this. As of right now, the current limit for delta gamma is around 2 times 10 to the negative 8th, but we calculated ACT's limit to actually be 8.5 times 10 to the negative 10th. So the ACT has potential to improve constraints on this type of equivalence principle violation by 2 orders of magnitude, and that is extremely significant. Next slide, please. So talking about the program itself, I really, really enjoyed this program. It was a fantastic way for me to spend my summer. And doing remote research within the COVID time, collaboration was something that we had to lean upon very heavily. I was constantly going back and forth with my mentor, Casey, colleagues and other scientists and physicists and astronomers and cosmologists and all kinds of people. We were placed in a lot of circles that I never would have been put in any other situation, so this was super valuable for me. I also gained a ton of coding knowledge using Python. I gained new cosmology knowledge, both in theory and practice, which is awesome for me. And on top of that, we had a ton of graduate school prep, which was amazing. It really made the whole process seem a lot less intimidating. And the scientist talks were not only extremely informative and interesting, but they were so inspiring. There's no way to quantify the benefit of a young Black scientist sitting in a room full of other Black scientists, but it is something that means so much to me, and I know it impacted every other scholar as well. So in terms of my project, looking forward to the future, I plan on continuing through the fall and maybe the spring as well. We'd like to develop more information about the source, allowing us to further refine results, and we'd like to investigate the effects of dispersion. In terms of the program, I think we should absolutely do this again next year. I think as long as you have the funding, this would be fantastic, and I think that every young Black physicist should have the chance of doing this. Thank you very much.
Okay, great. Thank you, Dante. So next up is James.
Hello, everybody. My name is James Truly. My mentor was Max Abitbull. Next slide, please. So I decided to put a little bit of my background on here. I started off as a biochem major, and I switched in the sophomore spring. So I'm now going into my senior year as a physics and dance double major at Hobart and Williamsburg colleges. I was part of a Rocksat C team where we designed a muon detector and put it on a payload that we launched at Wallops Flight Facility. That was part of the Colorado Space Grant Consortium. And so far, I mean, through this, I've been looking at grad schools that focus on particle physics. The more I learn, the more my would I want to do changes? Like now I'm thinking high energy, low energy, something around that. Next slide, please. So the primary science goal of Simon's Observatory is learning about inflation. And inflation generates gravitational waves, which in turn generate B-mode polarization in the CMB, which is measurable. Some of the main challenges of doing this are the fact that a signal is very faint. There are a lot of galactic foregrounds obscuring the CMB, like thermal dust, synchrotron radiation, and things like instrument systematics, like B-modes, or excuse me, beams. So for this project that I did, we studied the impact of a telescope beam on our ability to measure B-modes. So if you look on the right side, there's a true sky and a beam smooth observed sky. Sorry. Oops. So yeah, so beams will smooth out the image, and on my 10-minute presentation, there'll be more about that. Next slide, please. So I just sort of put everything together here on the last slide. It was like my thoughts in the program. I definitely was not a strong user of Python or any really coding language. So having the tutorials that were on Jupyter Notebook and also working with Max helped me out greatly. Having the opportunity to work with a physicist and their career paths is also great. And then just some feedback I had on the program itself. I'm more of a hands-on person. I like being in person. So being remote and behind a computer was challenging. It's also like very demanding as well compared to like being able to meet up in person. Also, I had some financial instability this summer, some personal things going on. So like the stipend not being dispersed immediately caused me to have to work more, and I missed out on a lot of our programming that we had, like the professional developments, which I was able to go back on the drive later and look at, but I feel like I didn't get to have the same experience because of my own personal issues. But also, like having this program in person, there's a lot of potential benefits, like being able to go to like sites either on like the East Coast, like the University of Pennsylvania or Princeton, or like the West Coast, like San Diego. And that's it. Thank you.
Great, thanks, James. Okay, so up next is Chimera.
Hi everyone, my name is Chimera Pruitt, and I double majored at Spelman College in math and physics. And my project this summer was painting gas on moving halos. You can go to the next slide. So yeah, like I said before, I'm painting gas profiles onto a catalog of dark matter halos. And the purpose of doing this is to study the resulting kinetic Sunyaev-Zeldovich maps. And what these are is just a distortion in the cosmic microwave background due to these free electrons in the halos. And I did this using a painting software called AstroPaint. And below is a picture of a simulated kinetic Sunyaev-Zeldovich signal from web sky simulations, which I will be comparing my data to. You can go to the next slide. So the way this AstroPaint works is it takes in a catalog of dark matter halos from the web sky data. And then it distributes these halos on a map. So if you look in figure 2, this is a 1 by 1 degree patch marking the centers of the halos. And then the last step is actually painting these gas profiles onto the halos. So the 2 gas profiles I use is the Navarro-Frank-White, which short terms is NFW profile, and then the Battaglia profile. So the main difference in these profiles is Battaglia has a fatter distribution of gas, and it is more similar to actual observations like at the Atacama Cosmology Telescope. So if you look at this figure 3, you see this blue line is more similar to the points for ACT. You can go to the next slide. So the main results that I'm receiving from this AstroPaint is the KSZ models. And this just models the density and the structure of these halos. And then to test the flexibility of these maps, I want to plot the power spectra of these KSZ maps and compare it with the previous simulations with the web sky. You can go to the next slide. And what this power spectrum is just, it just measures the temperature fluctuations over the variance in the angular space. And this L modes is connected to the variance in the angular space. And this is useful for studying the statistical properties of maps. So this figure 5 is the power spectrum from the web sky data, and then and figure 6 is the power spectra I created from the NFW and Battaglia profiles. And the most important results from this is that NFW has a higher power at higher L modes because of its cuspiness. And that just means it's more concentrated at the center. But for Battaglia, it's more core-like because it starts to flatten out at higher L modes. And this makes Battaglia a more ideal profile because there's less fluctuations on a smaller angular scale, which is what we want if we want to look at smaller structures like within galaxy clusters. So the big picture of this is there's very few power spectra of KSZ recorded, and Simon's Observatory is actually working to record the KSZ data because they want to know what the inside of galaxy clusters look like on the inside. You can go to the next slide. So yeah, what I've learned and enjoyed about this program is the opportunity to be exposed to research in the field of cosmology. The talks were very enlightening. I received a lot of great advice on what I want to do in the future. And I definitely want to go to grad school. And it's just made me feel like the sky's the limit for me. And I can do anything I set my mind to. You can go to the next slide. And I just wanted to say thank you. This was all made possible by Simon's Foundation and the NSBP. Also, thank you to my mentors, Siavash, Marcelo, Alexander, and George. They were very helpful and patient with me, and they taught me a lot during this program. Also, thank you to Casey for all you've done to make this program a success. And then the last slide is just my resources.
Great, thank you, Kimera.
You're welcome.
Okay, so up next is Darian.
Hi, everyone. My name is Darian Blakesley. My mentor was Bhuvnesh Jain. And so I just finished my undergrad at Arizona State in mechanical engineering. So it's been very new for me. But so I spent the summer mapping simulated clusters using Illustrious Python. And so if you can go to the next slide, please. Right, so I was looking at the intracluster medium, which is this very high ionized gas that fills the space between in these galaxy clusters. And they account for like around 10 times as much mass as the actual galaxies themselves. So they're a big part of the picture for kind of investigating the clusters. So could you go to the next slide, please? So I plotted the cluster gas for a subset of halos for an illustrious TNG data, and I got this data from Sam Goldstein, who's a student at UPenn. He helped me a lot with the coding and the details of this. So what I did was I mapped the position and the temperature and the density temperature relationship of these cluster gas. And so some of the things I was looking for was, like you'll see here, this offset of the center of the cluster mass, and and the gas and the gas mass. And then you'll see here at the plot below is this disturbed temperature distribution, which can help us kind of make some hypotheses of what's going on with this cluster itself, if it's merging or what have it. So next slide, please. So, okay, so then I looked at, I got more acquainted with Illustrious Python and actually pulled in density and temperature data from a large sample of halos for high and low mass halos, and compared how the density and the temperature related for these low mass and high mass clusters. And so I see that they kind of behave slightly different, and the low mass clusters behave more as you would expect in this, a lot more as you would expect, and these high mass clusters are definitely behaving different. So could you, oh, there's no more slides. But yeah, so this has been an awesome experience. Like I said, I'm a mechanic. My background is mechanical engineering. So this has all been very new for me. But I went into engineering because of my passion for physics. And so this has helped me kind of rekindle that passion. And coming into cosmology, I think one of the most uncomfortable things was not knowing what questions to ask. And at this point now, I'm kind of realizing what questions there are and really getting a sense of the bigger picture. And I really appreciate that. And I appreciate Casey and all the support. And so for the future, I'd really just hope to see students from all different backgrounds come in and kind of get their first hands-on experience with this stuff. And it's awesome. Thank you very much.
Great, thank you, Darian. All right, marching forward. Next up is Jonalyn.
Yes, good afternoon, everyone. Thank you for tuning in. We are in the middle of the Simons Foundation and National Society of Black Physicists inaugural Scholars Program finale. So I'm Jonalyn Fair. I'm a senior physics and math major, originally from Minneapolis, Minnesota, and I'm going to school. I'll be finishing up this December down here in Baton Rouge, Louisiana. My mentor was Dr. Anthony Pullen, and he works at New York University in New York, New York. Next slide, please. So this summer, it was a new experience with coding. I hadn't had any previous experience with Python and with Jupyter. I had previous experience with electrochemical and energy research, which was, it was very much material science, and I even made my graphs in Excel. So it was very code light. And this opportunity exposed me to Python code and also mathematical computational modeling. I was also able to collaborate and build a community online via Zoom, via Slack, with professors, peers, and also Simons Observatory scientists. So congratulations to all of the scholars, associates, and students in the program. We made it through a summer of COVID, and I feel like we performed extremely well under the amount of pressure that each of us experienced. So I sincerely hope to keep in touch with all of you as well. This program exposed me to basic cosmological principles in practice for the first time. So something very interesting about research is that you can collaborate with somebody who's doing the work in the field as opposed to learning about it in class as a concept and doing problems related to it. You're working on an actual problem. So that was very interesting. Also, I was exposed to theoretical physics, cosmology, astronomy, and astrochemistry, all fields that are not covered at my undergraduate institution. So it was completely new to me, and I was really, really happy to just be exposed to it as opposed to not. After this experience, I think I would like to go into this for my PhD, but we'll get to that. We also heard a lot of gems from wise and renowned scientists and also budding students, different graduate students who are well into their PhD programs. They were talking with us. We had Delilah Gates, and she talked with us, and she gave me a good example what you could achieve in physics and in astronomy. So representation definitely matters, and I was glad to be able to see them doing what I would like to do one day. Also, we learned about a lot of different astronomy research opportunities that exist beyond here, beyond this summer. So I've heard a lot of other students say they want to go and pursue their PhD. I do as well. And learning graduation, life after graduation tips, and also graduate school application tips. That's going to be extremely useful to all of us, I'd say. Also, I got some gap semester and gap year recommendations. I'll be graduating this December, not going to school in the spring yet, and then going back in the fall. So you can go to the next slide. And so what's next for me? So this is the conclusion of this NSBP program, NSBP Simons Observatory Scholars Program. And this summer, it was just a great experience overall. I have to say it was a great experience. Also, this fall, I'll be having my final semester of undergrad. I'll be applying to graduate schools. And this December, I'll be graduating, as I said, my degree in physics and math from Southern. Next spring, I'll be teaching virtual classes, tutoring, and applying to more graduate schools and fellowships. And then next fall, I'll be beginning graduate school, preferably a PhD program, but I'm also open to master's programs. And that's my contact info over there. Next slide. So next for the NSBP program, I'd say it depends if it's going to be virtual or in person, but definitely I'd recommend to do it again if you have the funding. I think it was a great experience for me this summer. Coronavirus kind of affects whether or not you guys can do it in person, but I think there was a little bit more to be experienced than walking past the hallway with your advisor. So maybe meeting daily, that would be a solution to that. A bit more structure to like having to how we meet, that would be useful. Also, I think that we should have sustained mentorship. So even though this summer was a great experience, I think that we should continue to talk with our mentors. We should establish a relationship between the scholar and prospective departments that they would like to go to graduate school in. And we were advised to do that anyway, which it was great advice. Before this summer, before I even got that advice, I thought, oh, maybe I shouldn't reach out. But I was encouraged by the stories of other people who are in graduate school. But yeah, it's good to reach out to those people before you just go into it. Next slide, please. So this is my research. It was modeling constraints for non-Gaussianity and primordial inflation using CMB lensing and galaxy clustering. It's my first experience with theoretical research, and more will be discussed in my 10-minute talk, so be sure to look out for that link. Next slide. Finally, I would like to thank everyone for the opportunity, mentorship, and also community. This was made possible by the Simons Foundation, funding from the Simons Foundation, the National Society of Black Physicists, my mentor, Dr. Pullen. Shout out to Dr. Casey Wagner, definitely helped out a lot this summer. And also thanks to the fellow scholars, associates, and students. And also last shout out to my mom, dad, and my grams for supporting me otherwise this summer.
Great, thank you, Jonalyn. All right, so marching on, the next person is Gile. So take it away.
Okay, hi guys, let me see. Yeah, next slide. Yeah, I'm Gilles, G-I-L-E-S. It's from French origin. I'm originally from Cameroon. Can you guys hear me loud and clear? Yes?
Yes, we can hear you.
Okay, yeah. I want to first slide. I want to thank all the the sponsors, the NSBP, KC, everyone was listed on the slide. I think it's a really good representation. I think I want to be clear that my presentation that I'm doing right now, it's specific to just sort of the finale of the program and everything I've learned from it. My research and details of that will be more specific in my 10-minute slide, 10-minute presentation that will be recorded and uploaded on the website that Casey would then give information about. But yeah, I think I learned so much from the program. I cannot say enough how grateful I've been to be able to participate in the program. I've learned a lot, and I've actually seeing like progress and even the benefits that come with it while in the program. And I'm just very grateful for all of that. So here I have a few names here. I think I want to definitely thank my mentor, Philip Moskoff, professor of physics and space and exploration in Arizona State University, and also his fellows, his Jacob Glasby and Eric Wicks, who helped me doing my who helped me, work on some simulations while doing the research that I was doing. And there's a few other people, especially Susan Clark, who's a professor who's starting off, I think, next year at Stanford, and she's also a physics professor. And she really, she was the one directing the graduate research workshops that we had during the program. And she gave us her email, and I reached out to her with my CV and SOP. And just a few days later, I got back a full 4 pages long, feedback essay basically, and that was the largest thing I've ever, and that was the greatest thing I've ever seen any professor or anyone really do for me, that really helped me even structure an SOP there and then. So I've already had my resume and my SOP, and I can literally apply to grad school the next day. And these are things that have happened to me within the program, and so I'm very much grateful for that, I think, overall. But yeah, other people that I included, of course, are the people within the guest speakers, the professional development host, and the social events that we had interacting with all of the mentors. And I want to also mention that I'm very grateful for everyone who I've met here. I think these are all networks that you gain within the program, and a lot of them you would not be able to get this much diversity within your typical college within physics as a Black student. So next slide. Yeah, so some program highlights include, so my research, I want to speak specifically my research. My research was looking into the development and application of the microwave superconducting quantum interference device, squared multiplexer, and that's all of that superconducting quantum, that's the micro MUX, that's what its acronym is. And then, right, how it's applied at the Simon Observatory, and looking at specifically how it's applied to the large and small aperture telescopes, and really diving more into the hardware aspect of it, of how that application is used to, collect photons that are being radiated from the sky, and collecting that information, and then transmitting it to data to then process it and make sense out of that data to how we, have all these other predictions about the universe. And right, other highlights include getting the license for AWR. AWR is a microwave office software where you're able to simulate a lot of circuits and RF designs. And I've had the opportunity to work with that to simulate some of the circuits that were used within the micromux that are used in these telescopes, and really get a better understanding of what's actually happening within, how do you go about communicating, like light to information overall. And right, and there's been a lot of workshops that happened within the program. I've listed a few here: Python, GitHub, and Git LaTeX, and even some things that, I think even some of the mentors have mentioned all the programs that they've used separate from what I've listed here, and some things that their mentor have introduced. And so you also get the opportunity to really diversify your skills. These are skills that you can also add to your resume. It really stands out. I think I've, being one who's always applying, always participating in different things, I've definitely seen the growth of getting new skills and adding them to your resume. The next slide. Yeah, so then for future plans, from here, I really do plan I really hope to do work on my research, continue the research that I'm currently doing. I do hope to dive much deeper into the physics. I've already done so in my 10-minute presentation, but I think I could definitely, there's still a lot to do. There's a lot of reading, and I think one of the things that I've definitely learned from my research is that you have to read. You really do have to read. The articles are long, intimidating, and there's equations that are, integrals that are very, even some of them are like complex analysis. And I've done the coursework, but it is challenging. But once you get a mathematical understanding, you really understand that it allows you to even add on to the research and really not just summarize what's going on. Right, let me see here. Right, so then the future plans are applying to grad school. I think I've really, like I said before, I've gained so much skills from this program that I can literally apply to the program. I'm very grateful for the program. I wanted to share some resources here while I have the chance. I think so. Listed on the picture on the right that I have here is some different programs that will fund grad school for physics and engineering programs that students are interested in. And so I do advise anyone. I do recommend people to look into it. I definitely plan to apply to Arizona State, which is the university that my advisor is teaching at, and right, you also get those connections and you're able to actually apply them to your own goals. And I'm just very overall very grateful, and I think that's all. Yeah, thank you.
Thanks, Shields. All right. So next up, we have Madison.
Hi, my name is Madison Allen, and this summer I got to work with Mark Halpern from the University of British Columbia as my mentor. And this project was basically on CGEM beam simulation. Next slide, please. Awesome. So CGEM is the Canadian Galactic Emission Mapper. And this device that we are creating, it measures the polarized sky to create the CMB foreground maps. So to create these maps, we first need to make simulation data. And for that data, we need to model a beam shape on the sky so that we simulate the experiment and we can make design decisions for CGEM. So in the image on the bottom, that's the CGEM logo. And basically, we're just rotating the telescope around as the Earth rotates to map the sky. Next slide, please. So we first start off with a co-polarized beam. And this beam is made from a Gaussian beam, and it has a set width and amplitude. So on the right, you see just a slice with this red dotted line through the Gaussian beam, and it has a amplitude in volts and across a distance of sine theta in radians. So it's a pretty small beam, actually. Next slide, please. So from that co-polarized beam, we have our parent function, and we take that parent function and make two of them so that when we displace them, we have, through a set distance, we are able to model a cross-polarized beam, And it creates this dipole image on the left. And as you can see from just another sliver, we have our two beams by a very small distance to place. And by differencing them, we create this cross-polarized image. And it has as you can see on the y-axis, has a very small amplitude compared to the amplitude of the original parent function. Next slide, please. And so as a result of this, we are able to create a beam shape to model the sky from these parameters of width, amplitude, and the separation. And so from this simulation, we are able to create the design for the CGEM and the future production of it. So basically from this program, I was able to meet so many physicists that I haven't had the opportunity to before, and especially Black physicists. And honestly, you really can't get there from many places. Originally, I was actually supposed to study abroad in New Zealand, but due to COVID, that was canceled. So I had an empty summer, and this opportunity came, so I jumped on it, and I'm so glad that I did. So I just want to thank my mentor, Mark, and Casey, definitely for a fantastic program. And I'm so excited to continue this research for my senior thesis and hopefully apply to grad school with this research. Thank you.
Great, thank you, Madison. So up next, we have Cameron.
Yes, so hey, people. My name is Cameron T. Jackson. I'm from the Steel City of Birmingham, Alabama. I am majoring in computer science, mathematics, and physics at the Grand Grambling State University. So I had the illustrious pleasure to work with Mr. Adrian Price Whelan, such a great guy at the Flatiron Institute. And basically, our project was characterizing the binary star system of KOI 466. You can head to the next slide. So can you load up everything? Is everything already loaded? There we go. There we go. And keep going. Should be one more. Yep. So basically, our project goal is, does the eclipse and binary star system KOI 466 have a brown dwarf companion, and what are its parameters? So when we're thinking in terms of parameters, we want to talk about the mass, we want to talk about the radius, we want to talk about the orbit, and we want to ask ourselves like certain essential questions that might follow behind that. And you can go to the next slide. Yeah, so what exactly is eclipse modeling, right? So the eclipse itself, what happens is you'll have the primary star, right? And then it'll be a secondary star, which is like a small, in our case, it would be a small brown dwarf, right? And what it would do is it would travel in front of the star and it will cause a drop in flux or the brightness. And ultimately, that's what we want to measure. Now, the problem that we're having along measuring this before we can get to the parameters is simply measuring the stellar variability that's when it, and then the reason, I don't know if y'all remember, but when Rebecca gave her presentation, she hit on the star spots that was coming in. So that's ultimately what causes this variability of a change in flux, a change in values, alongside the simple fact of having a star going from the next one. So can we go to the next one? Now, before I get into my phase folded eclipse, I actually want to hit on certain topics of what kind of methods did we actually use to be able to go in and like model this stellar variability. So at first we used the Savitsky Golay model, which is good for like modeling for like certain, I guess, periods. And in our case, we took like a 100-day period. But the problem was with that is we wanted a model for like almost 1,600 days, right? So then we switched over to a more fancier model, which was like the Gaussian process, and it actually modeled everything like beautifully. I wish I could share it right now, but what I'm gonna do is I'm actually waiting to give it to you on the 10-minute presentation. It's gonna be real nice. You're gonna love it. It's amazing. So then after we was able to go in and do the Gaussian process, which like I said, is great for modeling such a big change in variability, we went into the phase folded eclipse and we modeled before using the parameters. So then once we extracted the data within 0.25 days of the transit, what we had is, you can see the bullet points where I set up the stellar parameters, the Gaussian process noise model for amplification measures, and then planning and orbital parameters, and then optimization and other things. And you can click and shit back up another. Keep going, keep going. Yes. So then as you can see, we were able to go in and like create this beautiful phase folded eclipse model. And basically this model of this line shows you exactly what we want to look at, or exactly where we want to go. And from this, we were able to go and actually enter into like a nice little chart that gave us our radial velocity. Well, not radial velocity, but just our actual radius, I'm sorry. And then we gave us our radius, so we were able to figure out the radius, we were able to figure out the orbital parameters, but the one big thing that we wanted to focus on was the mass. So you can go to the next slide. Yes. So then we had our ideal comparison, right? So there was this nice paper that I had read over the summer, and it was Kanye's. And so basically, as you'll see this black line, our Jupiter radii actually came out to be 1.4. So that was the radius, right? Now, as you'll see, what they used in the Kanye's LL paper was the Kepler 503b. And Kepler 503b, of course, they were trying to do the same thing to see if they had like a brown dwarf companion. And you'll see this red line that like cuts right there. Anything to the right side of that red line, we would know that it would not have a brown dwarf companion. So this red line right here is actually very tentative, but it plays a crucial part in really defining where we might actually have a brown dwarf companion. So once we went in and calculated the radius, we was able to, okay, say if it lays on the left side of the line, it might be somewhere close to the Kepler 503b, and that way we can actually understand and see if it has that brown dwarf companion. Go to the next slide. And yeah, other than that, this is how do I feel. I will not read this whole thing, but generally I feel great about this. Like I said, I got a chance to work with Adrian. Such a great guy, such a warm character. Everything about him, like, it is just very enthusiastic. He actually introduced me to a smaller group and a lot of people at the CCA also. And I really enjoyed mingling and meeting with all these people because it was so much about them that was just, it was phenomenal to gain information from. Casey, I want to personally say thank you. This program that you tied together, it definitely helped with everything. It definitely, I feel like boosted my status as far as getting my interest inside of physics, because a lot of people know that I actually, when it comes to astronomy, I was like kind of in the loss, but I did know like the whole computing functions. I did know how to use Python programming, but to apply it in different measures and to actually like be comfortable with being uncomfortable, like that's a beautiful thing in itself. So then the final slide, I think that was it. Yes, and then ultimately just a big thank you, contact information at the bottom, and I just thank everybody from the bottom of my heart.
Great, thank you, Cameron. All right, we're in the home stretch. We've got 2 more presentations, and up next is Joe. So Joe, you want to take it away? Whoops.
Sure. Can everyone hear me okay? Yes, okay. Hello, everyone. My name is Joanne Roberts, and the goal of this summer's research was to learn 2 of 5 methods utilized in exoplanet hunting, which are radio velocity and astrometry. This included discovering, or for the sake of getting my feet wet, rediscovering a Jupiter-like exoplanet around the star HIP 11915 by plotting given RV data to create an RV curve model, then calculating the RV and astrometric signals. So for the sake of time, I will briefly go through the results, and any interested folk have the option to view a full recording of my presentation with a more in-depth analysis later. So the radio velocity method for detecting exoplanets relies on the fact that a star does not remain completely stationary when it is orbited by a planet. So we watch for wobble, since a star's wobble can indicate if it has any exoplanets. So what you see here is a plot of the RV curve. Using Jupyter Notebook, I was able to plot the HIP data and translate between the star's motion and what we observe, therefore calculating the RV of what we believe is a Jupiter-like planet orbiting that particular star. The curve is the model of the Keplerian motion that we optimized to fit the data, and we also had to normalize it for a better representation. The curve matches the data pretty well, as you can see. The period is about 10 years, and we know that Jupiter's period is similar to that. So judging from the wavelength, we concluded the data shows that we discovered a Jupiter-like exoplanet. And over 800 planets have been discovered using this method. Next slide. So the astrometric method for detecting exoplanets involves detecting the star's position wiggling around in space. So what you see here is a plot of the astrometric signal. Whether it's a wiggle or a circle depends on how the star is moving and has to do with where the observer is looking from. This is showing the proper motion where the observer is moving right alongside the star and they are staying relative to each other, which explains the lack of wiggle. We made it so the star isn't moving across the sky and the circle is due to the planet. Interesting fact, only 1 exoplanet has been discovered so far using astrometry because it is a very difficult method, but the Gaia missions will change this. So next slide. Aliens. If aliens were to discover like if they were, say, observing the solar system, our solar system, to discover planets, what would they be able to find? Which planets would be easiest for them to discover, and what kind of observations are needed? Most importantly, could they find us? And you'll have to tune into my full presentation to find out. Next slide. So in conclusion, I want to say thank you to NSBP, Simons Observatory, Casey Wagner, my wonderful mentor, Megan Bedell, and everyone else involved in making this such a great fellowship program. I am grateful that despite current events, I was able to spend the summer getting a feel for the scientist wings, I would say, are currently growing from my back. And I met some awesome people in the process. I finally learned some Python and have been reminded why discovery is the backbone of scientific exploration, as well as why this particular field of science influences nearly every aspect of my approach to life, from my creativity as an artist to my passions for teaching and, you know, my interest in seeing and traveling the world. I'm interested in doing more exoplanet hunting, as well as understanding neutron stars and black holes in graduate school. I feel this program has gotten me a step closer to my future in astrophysics and science education. So I'm very thankful. This includes my presentation, and what you see there is a book that I've published. It's an anthology of my poetry. So I'm offering signed copies to anyone who is interested. So just reach out to me. Yeah, and that's it. Thank you again. Last slide.
Okay, and we have one more. Rounding out strong, we have Emmanuel. So Emmanuel, you want to take it away?
Hello, nice to meet you, everyone. My name is Emmanuel Anecki, and I spent my SNSP experience working under the Flatiron Institute. Now, the hierarchy of the group I worked under goes like such. I have the Flatiron Institute up here, and then under that umbrella, we have the Center for Computational Astrophysics, and then there's a plasma group known as the Plasmaniacs. And my project was on reconnection. So now you must be wondering, what is reconnection? Next slide. To understand what reconnection is, we must first understand what a pulsar is. A pulsar is one of the potential remnants of a supernova, that big explosion that is, the death of a star. A pulsar is essentially a highly magnetized spinning neutron star that is constantly shooting out a beam of radiation and particles from its magnetic poles. So next you can see Next, you can see an image of a global simulation made by one of the graduate students amongst the Plasmaniacs hike. You can see on the leftmost image, you can see how a spinning object with things emitting out from either the top and side. As it spins, you have like this image of two colliding planes. So you get those wiggles on the x-axis. And then next, if you, next again, there you can see a localized 2D simulation of the development of the reconnection process. So the way it works is you have, what that is an image of is the darker shade is a higher density of particles, and the lighter shade is a higher density of particles. So there's a higher concentration of particles amongst the plasma, and where there's a darker shade, there's not so much. So one of the earlier images to the left, you can see dark spots, and those are called X points. So if you were to track like the lifetime of a particle, where it could start wherever, and then it flies into those dark shaded regions, the X points, and then it gets accelerated into those blobs, and those blobs are called plasmoids. And those plasmoids, the particles are just like all flying in there, and that's what we see. So then next, if we look at pre-existing pulsars, we see specific trends and shapes in the photon distributions. Because keep in mind, all we see are the photons. This is all, reverse speculation on like reconstructed speculation on what's going on up there. But all we see is the emitted radiation. And if we look carefully, we can see the red scatter plot is a Vela pulsar, and there's a slight increase in the photon distribution, and then it dips down, whilst the blue scatter plot, the Crab pulsar, is sort of plateaus, and then it dips down. And so what we know is that these particles exhibit this thing called synchrotron cooling. So when these particles amongst the plasma are like involved, they kind of get accelerated into the plasmoid. And when they get accelerated, they also spit out some of their energy. And that energy that they spit out is called synchrotron radiation. So if they're energized and then they also spit out some energy, they cool down, they relax. And that sigma value is basically telling us like, okay, most pulsars have like a similar particle distribution. They're generally made up of the same composition. However, the rate at which they emit synchrotron radiation is variable. And so that can affect the image of the photon distribution. So again, the Vela has Vela has increases and then dips off, and then Crab plateaus and then dips off. So the next slide. So in the simulations from the reconstruction that I did, we see that where there's stronger cooling, we have like in the blue line on the right side, we have an increase, but it's mainly a plateau, and then it dips off. And then for 200, the red line, it increases, it plateaus, and then dips off. So we got affirmation that the synchrotron cooling affects the shape of the photon distribution. Next slide. So I'm not going to read all that, but basically I just wanted to say that SNSP gave me the opportunity to, not only help my academic portfolio, but in a more social sense. Like this was a nice liaison into the world of not having to just work based on my own goals. Like science is bigger than us. It's bigger than the individual. Research involves more than just yourself. And so that it forces you to exercise good communication and maintain a good work ethic to collaborate with others. And as a member of NSBP Student Council, things like this is just perfect. It's what I want to see. And whether or not we decide to go remote or stay in person, I think this is a great opportunity for students being able to give NSBP students, you know, a holistic perspective on what it is to be a scientist. Thank you.
Great, thank you, Emmanuel. And we have one final speaker, and that's Anansa. And so let me go to Anansa's slides. Okay. So Anansa, if you want to, you're ready.
Yep. Hi, everyone. My name is Anansa. I'm a senior at USC studying physics. In my project during this.
Anansa, you got muted.
Oh, sorry. Next slide, please. Essentially, galaxy clusters are able to be observed at high redshifts, and the parameters surrounding those, the formation of those galaxies can tell us a lot about how our universe evolved. So things like dark matter clusters and matter content and matter density can tell us a lot about how the universe formed. So the purpose of this function, or before the purpose of this function, we were essentially able to run very expensive simulations of the universe to see how these galaxy clusters, or how these galaxies cluster. But the problem with those is that they're so expensive and computer intensive that we need to find a way how to run these programs or run a function that can do this that isn't so computer intensive. So essentially my product was to be able to find a way to simulate these galaxy clusters fast and to sample the mass function using both redshift and mass. So unfortunately, I can't show you any of the graphs from that because it is still a work in progress. But so yeah, but most importantly in this program, I learned how to use Python in a professional sense, which was a challenge specifically because of compatibility issues between Windows and Linux programming, which I didn't know that it would be such a struggle, but I had learned that it's very important for scientists to have, you know, compatible systems. But it was also a learning experience as to how we can get these programs to run on different systems, because the point of the function is to have this very accessible method of simulation. And also the program was very exciting for me because I have an interest in cosmology, and to see a lot of the concepts that I learned in previous semesters in being able to see what they are applied in research was really interesting. And as for what I expect to see in the future, I expect to continue this project. I can, you know, tinker with the code as much as I need to and see if I can, you know, help progress this, you know, fast forward simulation along. And I thought that the program was my first introduction to REUs, and especially in such a difficult time where we're not allowed to be, you know, together, but still in a collaborative environment. So yeah, I thought this program was really useful, and I really appreciated the time and effort that it took to put together. So yeah.
Okay, fantastic. Thank you, Anansa. I want to say, so that is the last of our scholars to speak. And I just personally want to say thank you to everyone. These were really fantastic. Some programming notes. What we're going to do now, we're going to hear some words from David Spergel, and then we're going to hear a thank you from Brian Keating. And then one of our scholars has a very special presentation and present for everyone. And that will be the thing that concludes our day. So David, would you like to go ahead?
Terrific. Let's see, do you want to turn off the screen? The slides, whoever's sharing slides, great. Wow, this was fabulous. I really feel I've seen a piece of the future of physics. It's just really exciting to see how much work got done, how much excellent science happened. I want to acknowledge a whole bunch of people. I want to start with first the students. It is really challenging to get anything done under this crazy COVID world. And you all managed to do a tremendous amount of science over the summer. And you should really all feel terrific. Want to thank the mentors. Great projects like this don't just happen. The mentors need to think of, well-defined, doable projects, work with the students, and it's clear from all the successes we've seen that the mentors for all of these projects put a lot of time, a lot of energy, a lot of thought, and thank you all. I particularly want to thank Casey. I actually want to ask all of the panelists to turn, all the students to turn their cameras on, turn their mute off for 1 minute, and let's just give like a round of applause to Casey, because he did just pulling this all together. Was fabulous. Just fabulous.
You don't have to. I appreciate it. I'm glad everybody
Thank you.
enjoyed it.
Thank you.
Good man, Casey.
Thank you so much, Casey. And let me also thank the other people who worked with me to put this together. This all started, I just can't believe this all came together with a phone call between Stefan and Brian and myself, imagining that, what could we do over the summer? We're talking about the fact that so many students were left without exciting science to do, without projects over the summer. I remember really well my own summer project working on modeling the atmosphere of Mars between the summer of my junior and senior year, and how important that was for me. I'll also note that one of the important things was just getting to meet the other people in my summer program. Some of whom, and this is something for you all to think to the future, some I've stayed in contact with, one for over 30 years. Not only that, I introduced him to the woman who had become his ex-wife. Think what you can do for each other. Want to thank Jim and Marilyn Simons. It's through their generosity with the Simons Foundation that we're able to make programs like this happen. And I want to thank the NSBP and for kind of bringing you all together and bringing you all into this program and making all this happen. Hearing your talks gives me a chance to teach you a word of Yiddish, kvelling. And kvelling is the sense of sort of pride in seeing the accomplishment of those you get to work with and those you get to honor. And that's how I feel hearing the tremendous science and really a lot of the great stuff you all did. I want to end actually my few minutes with a series of questions that we'll actually follow up with all the students and the mentors on. And I think we had this tremendous summer. I think hearing these talks, a lot got done. What do we do next? And I think I want you to think about that. What do we do next in a couple different ways? What do we do next with this cohort of students? What do you guys all do? How do we stay in touch? How do the mentors and the program continue to be a valuable resource, we hope, for you? What will be useful? What can we do going forward into the fall? And then also think about, you're all pioneers. You're the first year of this program. We want to do this again next year. How do we do it better? And we all need to think about, and this is a question I think all of us are asking through the pandemic, what are the things that we ended up having to do because of the pandemic, going remote, that we want to maintain some of the value of? I mean, one of the great things about this is we were able to connect, a student in California, with a mentor in Canada, right? I think we had one of our mentors often in Britain. We had people kind of connecting all over the country. And that's one of the great things about being remote and doing it this way. On the other hand, one of the things I think we're all missing is it would be great to get all of you together and have all of us together in one place. And how do we take advantage of the best of being remote, the best of being together. How should we think of formulating this program in summer 21? How do we grow it? I actually think this question of what do we take from the pandemic world that we had to do into the post-pandemic world is something we're all going to be asking about all different aspects of our lives. And I think for all of us, this has been a strange and difficult time, but some of the adjustments and some of the things we've had to do, I think open up new possibilities going forward, and we need to think all these through. I'm really excited about seeing the 10-minute talks. For the participants listening, we will be posting links to that, and people will get to hear more details about a lot of these really exciting projects, and we'll have those all up soon. And just end by thanking you all and just saying how exciting it was to see this tremendous amount of science that got done this summer, and to see the really promising scientists and what you've all accomplished. Let me turn it to Brian.
Thanks, David. I'm going to teach them a second word of Yiddish, and that's mensch. And I want to say that you and Stefan and Casey are three of the biggest mention. That means the plural of a great person. And it's been such a thrill to work with you guys. I'm here with my oldest son. I have 5 kids, as many of you know, and my youngest one is Emmanuel, so it's good that I go after Emmanuel. But I want to say that oftentimes I look back with my wife and I remember the very first son we had, Isaac, who's named after Isaac Newton, and he'd be crying. We didn't know what was going on with him, and I'd scream, "Get me the instruction manual," because you get no instructions when you get a kid, and those of you who have kids know that. And with you all, not that you're our kids in a way, but we really feel this kind of deep emotion towards you. And with kids, sometimes you mess up with the first one, and that was my fear. Remember, I asked you guys to have a good deal of forbearance and patience with us in this first year, and I think we learned as much from you guys as you did from us. And we really want to keep this going. As David said, we want to keep this going in the future. And you guys, as I keep saying, are our option, our call option on the future, which is just the greatest benefit that we can have. And if you can tell us how to improve, how to do better, that'll help the people that come after you. So want to express my gratitude to Jim and Marilyn Simons, who have been behind this, following in the background. You don't know how much pride they have in you guys, but they express it to me and to David and to Stefan extremely often. This is a real capstone for the foundation, and you guys just did such a tremendous job. I'm really overwhelmed, and I can't wait for the NSBP program when we can all show up from the Simons Observatory and make our pitch to you guys to come to our universities and institutions for graduate school, if that's where your plans may take you. I want to conclude with one more Judaic reference, and that's from a very famous rabbi, a leader in the Jewish world named Menachem Mendel Schneerson, the Lubavitcher Rebbe, and he said about leaders, he said once that a good leader creates many followers, but a great leader creates many leaders. And I'm looking to you guys to be the leaders of the future, not just in the NSBP and in your cohort, but in astronomy and astrophysics in general. We really have tremendous hopes and expectations because you guys are so phenomenal. I want to thank you guys again. Please keep in touch. You can find me anywhere on the web. I'd love to stay in touch and hopefully convince you to come to sunny San Diego someday. So I'm going to run and take care of the other 4 kids. And I want to say thank you again. Big thanks to Casey. He did a tremendous job under tremendous pressure. Thanks to Stefan, David, the staff at CCA, staff at UCSD, staff at the NSBP. It was really just an unbelievable experience for me. And I'm hoping this will be a model for future programs like this. Thank you all so much.
Okay, great. Thank you, Brian and David. So I think that we're getting near the end of today's program. And to close it out, we have a special contribution from one of our scholars. And so, Joe, you want to take it away?
Sure. So with everything that's been happening in the world, there's been a lot of death, destruction, rioting, depression, stress. and just a general feeling of uncertainty. And usually the way that I get through hard times is by writing. I am a creative person, and I wanted to share this piece as kind of an ode to this summer's work and the work that I was able to do with other folks. And it's a liberation piece and a healing piece, and I hope that it reaches you all very well. The poem is untitled, but I'll just get into it. And I'm guessing everyone can hear me, correct?
Yes.
Yes.
Okay.
Yep.
Okay. Well, I want some feedback on what I should name this piece. So if anyone has any suggestions when I get to the end, just reach out to me because it's untitled for now. At the event horizon of a black hole, there's been a rising of black souls. We arrived in time capsules. We are the masterminds. Forward, fast rewind, viewing stars from past design. We are the last to shine, a mysterious class divine. These dark matters have beginnings in the origins of originality. We are just now earning our winnings, but we were here before the galaxies. An argument full of fallacy, but what you believe becomes reality. And what's in us is in the stars. So I view our history through this analogy. All that is old is new, and all that is new is old. Our sun has told the truth, reflecting seas of blue to gold. We are neglected as a collective, yet we possess these star qualities. I'm so invested in this perspective, earthed at center like Ptolemy. With silent Big Bangs preferred, like when the Big Bang occurred. These are times of civil unrest, where now Big Bangs are heard. From that of the celestial sphere, we are the extraterrestrials here. We arrived from frozen suns, burning wild, the chosen ones. Among wildfires burning slow, we're enduring constant struggle. Turning whole via wormholes, we expand like constant Hubble. We are infinite yet finite, bringers of dawn and twilight. Sparking bright like pyrite, we came alive before we arrived. A monolith of afterthoughts, but we're layered like Earth's core. Take off, explore like astronauts. We are truly before. Without our dark energy, the universe would collapse into itself. We are the entities of that chemistry, bodies holding place like the Kuiper belt. The distinction between you and I remains to be a false dichotomy, for at the heart of purest life lies a beautiful geometry. Through devastation comes celebration, for our wealth lies within astronomy. Yet many beings look down at night, aligned with what's suitable for man's economy. A virus claiming its older victims, I must look to the sky for solace, for we are all of the solar system, earthly flawed, but cosmically flawless. Are we nearing our 11th hour? Will we fold under this pressure? With nature feeling our powers, we can change the world like Tesla. Make a life, but one can take it. Bullets fly, but we're the matrix. This is scientific, but also sacred, as no one ever truly dies. Through portals, we become immortal. I know now what my calling is. I gaze the star for reminders. We're survivors, much greater than all of this. Thank you.
Thank you. That was awesome.
Fantastic. There's no better way to end this program. So thank you, Joe. And thanks to everyone, and we'll be in touch.